Alright, good morning. That was weird. I started the Zoom session about 10 minutes ago, and then I just checked and there was nobody there. And I either started the wrong session or something glitched out. So I closed it and restarted, and people were there. I upgraded Zoom over the weekend, so there could be some weirdness. But so far it seems to work well. Alright, how is everybody? Good. And that means I have audio working. Well, hopefully everybody had a good few days of break. And got caught up on whatever you needed to get caught up on. And we are up to our last week now. This is week 11, so amazingly, we're at the end of the course. And that feels really fast to me. But it's been a weird year anyway. But all right, so any questions up to here? Questions on what we've done so far? Questions about Bash, things like that. My plan is to talk a little more about processes today and go into some other stuff tomorrow, and then towards the end of the week talk about the final exam and sort of the course wrap up. So a few comments up front about the final, and I haven't written the final yet, so I can't really speak to what's going to be on it. But general comments, right? Your final exam will be Wednesday at 11 o'clock, right? So check the Clark website for exam schedules for presumably all of your classes. But ours should be Wednesday at 11. I'm going to double check that right now. It's whatever's on Canvas. So it'll be a Canvas quiz, just like the midterm. It will probably entirely look like essay questions that you type the answers into, just like the midterm. I don't know if I'm going to put some actual multiple choice on there. It's possible, but I'm thinking right now probably not. Interesting. December. Aha, okay, yeah, Wednesday, 11 o'clock. And it will be largely programming questions, but there may be more shorter questions as opposed to just a few really large ones. But we'll talk about it more towards the end when I've actually written it. But basically, you know, be up to speed on programming, both C and Bash, and also, you know, all the stuff in Linux that you've presumably been using for the past 2.5 months. So the exam is scheduled for an hour and 50 minutes, so 11 o'clock to 12:50. I'll try to target it to be doable in about, you know, an hour 20, so I'll try to leave like a half-hour wiggle room in there. But, you know, these things are approximate, so you'll have an hour 50 to do it. And it's got to be taken at, you know, starting at 11 o'clock. It's not like you can just come in anytime during the day and do it. It's actually scheduled 11 o'clock to 12:50. And that's Wednesday the 9th, correct? Very cool. And yeah, I'm going to ask you not to use any outside resources, including compilers, syntax checking editors, and so on and so forth. If you want to type your code into Notepad or something, right, and then copy and paste it from there into Canvas, that's fine. But no technology to assist you with writing your code or testing your code or validating your code, and no, you know, resources other than your book and your notes. No Googling, stuff like that. All right. So a couple of comments regarding grades. So number one, as I think we mentioned last week, there's no service learning project for this quarter. So the SLP, which was 5% of your total grade, everybody's going to get 100% for their SLP component. Okay, so that's just kind of a rounding bonus. So everyone gets 100% for that. Yeah, cool. Nice work on the SLP, everyone. The 5 programming assignments, I've told you I will drop the lowest grade. So what's going to happen is I'm going to adjust the grading to count to ignore ungraded things rather than count them as zeros. Okay, and then whatever your lowest grade was will be deleted, and will show up in the grade book as missing, which means that Canvas should not calculate it into the final average. So if you got 100 on all 5 assignments, you're going to see one of those disappear, right? Don't panic. It's disappearing so that it doesn't count. And I'll save the grades before I make that adjustment. And then everything else grade-wise should look, you know, exactly the way it is in Canvas. And something else I wanted to say on that. Oh, the other thing is, you know, usually there's some sort of nominal curving that takes place at the end. The curve will never work against you, but if you go to angrcs.com, look at the department policies, you'll see, you know, translations from numeric grades to letter grades, and those will probably get adjusted at least a little bit. So if I don't know what a C starts at, let's say it starts at 73 right now. It may be I'll change that and the C will start, you know, let's say a 65 or something. But I won't curve the other direction. Hello. I won't curve the other direction in a way that harms you. But usually there's some kind of adjustment. My general advice at this point is try not to worry about the grades. Okay? Try to spend your energy and time thinking about, you know, programming, algorithms, figuring out the things that you're not as strong in, and, you know, asking questions about that, and then also concepts, right? Just keep working in Unix. Try to be as comfortable as you can with basic Unix operations. Anything you're not very comfortable with, Git, etc., right? Just go ahead and review that, ask questions. I want to finish talking about processes today and maybe tomorrow. I still want to talk a little bit about awk, but, you know, more than any of that, I want to, you know, have people ask questions and talk about those. So if we wanted to spend the entire week just doing that kind of review, that's fantastic, right? From this point forward, anything that I'm going to talk about is stuff that you'll see again in other courses. So think about the stuff and ask questions, right? And we can definitely talk about that as much as people want to. So there may be some conceptual questions on the final about processes. I'm not going to have you writing code because we haven't done that. We haven't done assignments with it and such. But yeah, I'd like you to know, that a fork is used to create a clone of your process, and that fork returns, either a 0 for the child or a process ID if you're the parent. We'll dabble with exec a bit, so you should at least have heard, execl, execv, that kind of thing, and know that they're somehow used to change what a process does. And we'll play with some code for that in a minute. And we're going to talk about pipes, and I'm probably not going to ask you anything about pipes. So I want you to know the high level concepts, but no, we're not going to get into any coding like that on the exam, or anything very detailed. And again, that's all stuff that you're going to see again in other courses. So let's play with execl. We messed around with this a little bit at the end of last week. So let's do a quick refresh here. Integer main, I'm ready to call execl, and I'm going to make a call to it, and I'm going to give it an argument of /bin/date, a second argument of bin date, a third argument of null, and then I'm going to print out done. All right, and I asked this question in the previous section, so let's go ahead and talk about this also. Why do I have this include statement here, right? If I don't have this include statement here, I get warning messages, right? So I have to put this include in here. But what is that for? What is that actually doing? What's the reason of doing the include? Yeah, so you probably mean prototypes, right? So yeah, this is doing what we call prototyping the function, right? What does that mean? Here's a main program. It's called main. Here's the code which makes up main. So after I run this through the compiler knows exactly everything there is to know about this function called main. In particular, it takes no arguments. It returns an integer. As part of that compilation, I'm calling this function printf. Well, here I'm calling it with a string. Somewhere else I might be calling it with a string followed by an integer. I don't seem to be doing anything with the return value, but somewhere else I might do something with the return value. So what is this thing printf? It's clearly a function, but how many arguments does it take? What types of arguments? What types of things does it return? Right? If the compiler doesn't know that, it can't write proper code to use this function, right? So this is, you know, you're going to build a house, and you've got to leave room for the sink in the kitchen, right? Well, you know, how big is the sink? Where do the pipes come in for the faucets? Is the hot water on the left or the right? How much counter space do I need for the basin of the sink, right? You don't actually have your hands on the sink yet, but you still want to build the kitchen. And you just want to leave a hole there, and then when the sink shows up, you just pop it in and hook up the pipes, right? So this is a description of the kitchen I'm building, and it's saying, you know, I'm going to have a sink called printf. And we don't have the code for this yet, but we need to know a little bit about it. Right? We need to know what types of arguments does it take, what type of value does it return. So that's why we prototype the function. And the prototype is like, you know, the specifications on the kitchen sink, which says, you know, it's this many inches by that many inches, and it's this deep, and it needs, you know, this kind of piping to connect to it. So if we're writing a function ourselves, we put a prototype here. We would say, you know, integer my function parentheses int comma car star, right? But these functions printf, execl, we haven't written those, so we get the prototypes from somewhere else. Well, printf, the prototype is in standard IO. Execl, which is not something we use every day, the prototype for that is in a different file called unistandard.h. So The angle brackets mean, let's look under /usr/include. And then unistandard.h is the name of the include file. So we can look at that. It's, 1100 plus lines of stuff that looks like this. But we can search for execl, and there it is right there. Right? There's even a comment in there. Execute path with all arguments after path until a null pointer and environment from environ. I don't know what that means, but they used two kinds of quotation marks, so it must be meaningful. But it tells us execl is something that returns an integer. It takes an argument, which is a char star. It takes a second argument, which is a char star. And then it uses something called var args, which are these ... dots, which say there could be multiple arguments after that. And it also has this word extern. And extern says, I'm prototyping the function here, but I'm not going to show you the code for it. You're going to find that elsewhere. So somebody asked, how are these files linked since we don't link them manually? Really good question. So where does the actual code from this come from? It comes from something called a library. And there are different libraries available on Linux, but when we just say gcc, filename.c, there's a standard library, and the system will always look in that standard library for whatever functions we need that have been declared external. For example, execl, printf, things like that. And there's different libraries for different functions. So when we say something like gcc-o main.c-lm, right? What we're saying is, okay, I want to run this program called gcc. We know this is saying call the output file main, the executable. This is the file I want to compile. GCC is a program. It'll open this file, read it in. It'll say, oh, integer A, okay, A is an integer, etc. This thing over here, remember, if we do something like, square root, we have to put a -lm at the end. Okay, -l is a switch, which means include a library, and m means look for a library called libm.a. If we did a -l haha, I would look for a library called libhaha.a. Alright, now these libraries are stored in the system. They're available as part of Linux. And we can find those. And you can set up, different environment variables that tell you where these things might be located, but the standard location for these things is /user/lib. And if you look in here, there's a whole bunch of files. And there's a bunch of directories. And if we go under x86, 64, Linux GNU, so x86 usually means 32 bits, 64 means 64 bits. So this is a directory containing, different versions of these files. And inside here, there's, a bunch of other stuff. There's a bunch of .a's. There's a libz, there's a libxt, there's a libcd-present, right? Each of these things can be pulled in by saying -l followed by, whatever comes after the lib. And down here is a libm.a. And that actually refers internally to this library called libm 2.27. That's the current version of the math library. And a .a file is an archive. It's like a tar file, but it's meant to be written to a file instead of a tape. So it's just an AR instead of a TAR. And we can use the AR command just like we use tar ARTV, and we can look at We can look at libm 2.27.a, and inside this archive is a bunch of .o files. And what are .o files? Well, .o files are the things you get when you compile and you say gcc-c. If you compile file.c with a -c switch, you get a file.o. So you want to calculate the sine of an angle. You call the sine function. Well, that's a function written in C. And whoever wrote that, at some point somebody said gcc-c file.c. They compiled it into an object file, a .o file. And we know that, we could list, our .o files in our gcc command. But we don't want to do that. We don't want to know where these files are located. We don't want to have to put in the big long paths to them and so on. So these are all bundled up into this library. And when we say gcc-l, name of a library, what happens is the linker, when it's looking for this executable code, will look in that archive for whatever .o files it needs. If there's a file it doesn't need, it ignores it. But if it's looking for, file.o, it'll search through there, find the contents of file.o, and then pull that in and use it in the linking process. So all of these .o files are potentially available when we say -lm. And there's gamma products, if you like gamma functions, and there's I don't even know what some of these things do. There's lots of logarithms. There's inverse hyperbolic sine, single precision floating point. There's a arctangent, single precision floating point, and so on and so forth. And there's sines and cosines in here, right? There's the square root function, one of the square root functions. And the prototypes for these, we're in the user include math.h. Sign's hard to find because it's part of. And I'm guessing this includes other files that actually have the interesting stuff. But somewhere, if you follow this train of inclusions, right, you actually find the prototypes for these functions, and then the actual code for the functions is contained in, these different .o files. And you can pull these out, right? You can extract them just like you can from a tar file and have a .o file, and you can link to that, right? Or you can reverse engineer it if you want. You can look at the ones and zeros and turn it into assembly language and figure out, how the sine function works. Which raises the next question. How does the sine function work? Or the logarithm function or the exponent function. How does this work? It's a C program. It's just, written with stuff that you learned in CSE224B. How would you write a program to calculate the sine of an angle? There's lots of sine functions in here. I am going to get SpongeBob money for winter and hand it out to people. Alright, desert island, how do you calculate sine of an angle? You've got a calculator, but it doesn't do sines, it just does add, subtract, multiply, divide. Any guesses? Not a clue. Not without the sign button. These are good things to ponder. Because, you know, that sign button wasn't always there. And worse yet, it may not always be there. I mean, we could do this with pencil and paper, and we could make a sheet of graph paper, and we could calculate it by you know, using a triangle. But that's probably not what goes on inside a computer. There's a formula that uses pi and some complex math. Good, yes. Going in the right direction. Isn't it a circular function? It's related to circles. I wish people had their microphones on so I could hear the collective groan when I show you this. Taylor series. Anybody ever hear of these? I got one groan locally. Oh God, there we go. Okay. Yeah. So we don't teach these things just to, you know, be mean. Taylor series are really useful. They're a way that we can calculate these complex functions, transcendental functions, things that don't even have, you know, rational or algebraic values, but we can calculate them using pretty simple arithmetic, right? Now getting here, that's all the calculus stuff, right? But once you have this formula for a sign, it's a bunch of multiplications, divisions, additions, subtractions. And this is how most machines calculate trigonometric functions, or logarithmic or exponentials. They use a Taylor series or something equivalent to that. So the ... means go on forever, but we don't have to actually do that. Right? If we're out in the 15th term of this series, the 15th term we're probably dividing by around 31 factorial. That's a big number. And you know, if x is pretty small, x to the 15th is still pretty small. It's probably smaller than 1. And 1 divided by, you know, 31 factorial, we don't even have to worry about that. So the functions go forever, but when we calculate them with, you know, a little for loop inside a C program, I don't know, we might go out 15 terms, maybe less than that. In practice, you probably go out until this piece that you're about to add to your running sum is small enough to ignore. So you can sort of dynamically adjust it, especially for things like exponentials that aren't bounded. And if you take a course in numerical methods, this is part of the stuff that you'll study, right? This gets into all of the nuance about, you know, if we go out this many terms, can we say what the maximum error is that's possible? Or if we want a maximum error no bigger than this, how many terms do we have to go out to guarantee that? But, you know, for desert island purposes, you know, 10 or 15 terms, who cares if you do 20 and you only needed to do 15? 5 extra iterations in a for loop, not a big deal, right? But basically, you just, you know, multiply and divide and add and subtract, and there's your answer. And you can write that in C, right? It would take you, you know, probably 10 minutes to write a for loop to do this calculation. You can make your own sign function. And then you compile it into a .o and you put it in the library, and you've, you know, replicated the math library. All right, and one thing I'll just mention here, one final piece, calculating polynomials efficiently. So suppose you want to calculate that polynomial. All right, calculating x to the 4th, that takes 3 multiplications times 5 is 4 multiplications. This is going to be another 3 multiplications. This is going to be 2 multiplications. This is going to be 1 multiplication. That's going to be 10 multiplies. And then you have to do a subtraction, addition, subtraction, addition. It's going to be 4. additions and subtractions. And this number is growing by n squared, right? If we've got to go out to x to the 15th, that's going to be 15 multiplications, and x to the 14th will be 14, and so on and so on. It turns out there's a really neat little trick you can use to calculate a polynomial like this, and this is used by most of these algorithms. And it's not such a big deal today because, you know, our machines are pretty fast, but when floating point multiplications were really expensive, this was a huge time saver. So you've got a value for x and you want to calculate the value of this polynomial. Well, here's something you can do. You can take 5, multiply by x, subtract 7, take that result, multiply by x, add 2, take that result, multiply by x, subtract 9, take that result, multiply by x, and then add 10. And if you work this out, this becomes 5x squared minus 7x. And you can add a 2 here. And if you take that and you multiply by x, you get 5x cubed minus 7x squared plus 2x. And then you subtract 9 and you multiply by x, and you get 5x to the 4th minus 7x cubed plus 2x squared minus 9x. And then you add a 10 at the end. The nice thing about doing your calculation like this, though, is what do? You do a multiply, a subtract, a multiply and add, a multiply, subtract, a multiply and an add. It's 4 multiplies, 4 adds, subtracts. And it's a much more efficient way to calculate polynomials. Now, why would you care about doing it like this? If you were writing a C program, you probably wouldn't, right? You'd be done writing your basic for loop that just calculates each of these things and adds them together before you finish this analysis. But imagine Engineering 250, you're in the lab, you've got your box of parts and your proto boards, and you're trying to build a circuit to evaluate this polynomial. Right? Do you want to build a circuit to calculate x to the 4th and x to the cubed and x to the squared and so on and so forth, and then do all these multiplies and adds? Or do you want to just do this one thing? Multiply, add, multiply, add, multiply, add, multiply, add. All right? So when you were actually designing hardware to do this, this is a whole lot easier to implement, and it's faster. Right? It does less work. All right. So that's a bit of sidebar, but it's good. All right. So let's go back to our function. So let's play with this exec function. So we're going to say ready to call exec, we're going to exec bin date, and then we're going to say done. And we're including unistandard so we don't get warnings. And if we run this, it says ready to call execl, it prints out the date. The notable thing is it never printed out this done message. So ready to call execl, it printed out the date, and then it exited. All right, and this is the key thing about exec. And there's different versions, I'll just call them exec. The key thing about exec is it's not saying, you know, go ahead and execute this function, let me know when you're done. It's actually changing the current process into effectively this program. So exec opens up this file, right, something like an fopen, and it starts reading out the bytes from that file, and it finds the executable code, the ones and zeros that resulted when, you know, date.c was compiled, and it loads those ones and zeros into its memory. And when exec is done, none of this remains. When exec is done, the process that's running is now executing the code that came from /bin/date. Right? It's completely morphed itself. It's like exec says, okay, go ahead and take my brain and replace it with the brain from /bin/date. Right? And you write on your calendar, okay, so first I'm going to, drop off my dry cleaning, and then I'm going to do an exec on bin date, and then I'm going to walk the dog, right? Well, after you finish this exec, which says replace my brain with the brain from bin date, am I still going to walk the dog? No, because that part of my instructions is not part of the brain that just popped into my head, right? I have an entirely different process after this exec executes, and this print done, that's nowhere in the memory of this process anymore. It's a completely new process. Okay, so that's the kind of creepy way the processes specialize. So it's a two-step operation. First we do a fork, which makes a clone of the current process. And if that's all we did, then we'd have 300 of the same process running around, each claiming that they were the original, right? So after the fork, after the clone is made, the clone changes its essence. It uses an exec call to change it into a process that's doing something different. And that's why we have 300 distinct processes doing different things on the system instead of 300 clones. Let's see, question. Are there security issues and or lots of bugs in this kind of memory and instruction replacement with exec? Lots of potential bugs when you're writing code to do this, absolutely. You have to know what you're doing to make this work right, but no more so than using a scanf or an fgets or anything else. Security issues, not really. No more than anything else. It's a very solid way of creating and manipulating processes, actually. But that, I'm not going to say there's no exploits that take advantage of something in this, or that there haven't been in the past. But even though it's a kind of hairy operation, I don't think there's anything in particular about this that's a security concern. But it is kind of weird to think about, right? It's an unusual way to do things. So typically we would have a process. It would do a fork, and then the child typically would exec and become something new. So when does this happen? When I type a command on the command line, for example, I say date, and it shows me the date. Well, how did that happen? Bash doesn't know anything about the word date. There's no code inside Bash which says, if the person types date, let's figure out how much time has passed since January 1st, 70, and let's turn it into a month, day of the week, etc., right? That's not part of Bash. But there's a file called date.c that got compiled into something called date, which is sitting under /bin. So Bash is sitting here, right? It's at the command prompt. It's saying, hey, Nick, what do you want to do? I type in date and hit enter. What does Bash do? It checks to see if there's a file called date somewhere. So it looks at that path variable, right? Remember, we have this thing which says, where should we look for commands? And it says, well, let's look in the current directory, use your local sbin, use your local bin, use your sbin, use your bin, sbin, and /bin. When it gets to /bin, it does find a date in there, and it finds that file's executable. And it says, okay, we're going to run this for Nick. So what does Bash do? It calls fork, and it makes a new process. Copy of Bash. Right? So now there's two Bash shells running for a moment. But the copy knows that it's a copy because its return value from fork was 0. And it says, oh, I'm the copy. I'm supposed to do something. What was I supposed to do? Oh, yeah, I'm supposed to do /bin/date. And it basically executes a call to exec with an argument of /bin/date. And now this clone, which was running Bash a moment ago, suddenly is running /bin/date. and that calculates the current date time, puts it into a string, sends it to standard out, which is the same standard out that my original bash process had, and then it exits. The original process, which called fork to create the child, has been monitoring the child, and when that child process exits, my original shell says, oh, that command is done, and it prints out the prompt, and it goes back to waiting for a new command. So this isn't, you know, just some weird, bizarre thing we can play with to learn about processes. This is how everything happens on Linux. This is how these things come into being. Every time you type a command that's not a built-in function in bash, this is what's happening. All right, so let's leave exec for a moment, and let's talk about communicating between two processes. Okay, so this is the idea of a pipe, and we know about pipes. You know, in this sense, we can type a command, we can say pipe into something else, and it'll tell us date outputted 29 characters. But we can use pipes at a low level inside inside our C code. So here's some other sample code. So I'm going to have two processes. I'm going to make a call to fork. I'm going to save the return value in a variable called PID. And if that variable is equal to 0, it means I'm the child. I'm going to call a child process, right? Just a function called child. Otherwise, I'm going to call a function called parent. So I'm going to split the behavior of this program up into two function calls, one for parent, one for child. And what I want to do is allow these two processes, which are independent of each other, to communicate with one another. And the way we're going to do this is with a pipe. So before we fork, we're going to create a pipe. And you can think of it as a conduit. And there's two ends. There's an end that we can write into and an end that we can read from. And what we're going to do is we're going to set things up so that the parent is going to write into one end of the pipe, and the child is going to read from the other end. And since this pipe was created before the clone appeared, right, both parent and child, when they think about the pipe, they're thinking about the exact same pipe, which means when the parent writes into this side and the child reads from that side, it's going to read whatever the parent wrote. So this is going to set up a communication path between the two processes. So pipe is a system call, chapter 2, so low-level system call, takes an argument which is an array of two integers. All right, so we pass it an array of two integers, and it will fill in values for those two integers. And the meaning of those integers is, so if we say integer fd bracket 2, that's short for file descriptor, and we call pipe with fd. fd bracket 1 will tell us how to get a hold of this end of the pipe. fd bracket 0 will tell us how to get a hold of that end of the pipe. And since these are file descriptors, right, low-level things, we're not going to use printf and fgets. We're going to use read and write. So the write function takes three arguments. It takes a file descriptor, which is an integer. It takes an array of characters, and then a count for how many bytes we want to send. And the low-level counterpart, read, same thing. Takes a file descriptor, which is an integer, an array of characters, and how many characters we are willing to read. Right, so this is the size of the buffer. And read actually returns the number of bytes that were read. Alright, so what does this look like in code? Here's my file descriptor. Okay, it's an array of two integers. Here's where I call pipe, which fills values into both ends of FD, both elements of FD. So we can print these out here. right? And what we'll see is FD bracket 0 ends up being 3 and bracket 1 ends up being 4. They're just, usually consecutive integers. They reference some sort of internal structure. So here's where I split off into a parent and a child, a clone. And if the fork returns a 0, I'm going to say I'm the child, and I'll call this function called child. Otherwise, I'll call parent. And I'm going to pass this array of integers, fd, to both of these functions. Because that array, right, that's how I know how to access the two ends of the pipe. And so the parent process is just going to send something into the pipe. Well, it's going to sleep a few seconds first. And then it's going to write hello followed by a new line into FD bracket 1. That's the end of the pipe that you write into. Okay, that's just the convention. And I'm going to write 7 bytes. Why am I writing 7 bytes? HELLO, that's 5. I'm going to put a new line on the end just for kicks, that's 6. And then I'm going to put a null terminator at the end, that's 7. Alright, so I'm going to write that in, and then I'm just going to, return, which will exit the parent. The child, it'll say I'm the child, it'll say it's reading from the parent, it's going to call read, it's going to read from FD bracket 0, that's the read end of the pipe, and I'm going to pass it the address of a character array, and say you can read up to 120 characters. But I'm going to save the return value from read in an integer called result that tells me how many bytes were read. I'll print out the value of result, and then we'll go through a for loop and print out each character of the buffer, showing the value of the first result characters. So this is basic inter-process communication. Here's our main process. We create a pipe, and then we fork a clone, which is the child, and now the child and the parent have the same pipe, right? It's exactly the same object, and if the parent writes into this end, the child can read from that end. So let's just go ahead and run that, and then we're out of time. Right? So 2 processes, the parent already wrote, it's sleeping right now, the child's waiting, the sleep expires, and the child reads, and read returns 7, and there's a 7 bytes it found. HELLO, those are ASCII codes. A 10, which is ASCII code for a new line, and then there's the null terminator. And yeah, this is basically how multi-processing works. Multi-threading on processors is a little different, though. That's a lower level activity, but this could take advantage of multi-threading in a processor to run things in parallel. Let's see, question, what online course do you recommend for further learn Bash and Unix? I don't know any good online courses. A few of them got mentioned in discussion, linuxjourney.com. I haven't looked at that. But I'm hoping we can spend, the rest of this week answering questions, right? So if you have questions, let's talk about them in class. Everything I'm planning to talk about from here until the end of the course is stuff you'll see again. Right, so if we have questions, on any of this stuff, let's talk about them in class. That would be a great use of class time. All right, so I'll talk a little more about processes tomorrow, and I'll loop back and talk a little bit about awk, and we'll be wrapping things up. Have a great afternoon. Enjoy the rain, and I will see you next time. All right, thanks.